This is the beginning of section 9.4. It is about the inferences from two samples, and whereas section 9.3 had to do with two samples that were independent, section 9.4 is about two dependent samples, also called matched pairs. So recall that two samples are independent if the sample selected from one population is not related to the sample selected from a second population. However, two samples are dependent if each member of one sample corresponds to a member of the other sample. So that's a distinction. And then, as I mentioned before, dependent samples are also called matched pairs samples. So a hypothesis test for the difference of two means is a paired t-test. And that works if two samples are randomly selected, if both populations are normally distributed, or both samples are large, in other words, where n is greater than or equal to 30, and if the two samples are dependent, or also called paired. So here the test statistic t is d bar divided by the standard deviation for the test. Standard deviation for the test. And that's equal to d bar divided by s sub d bar divided by the square root of n. That's d bar. The sample standard deviation of d bar divided by the square root of n. With degrees of freedom equal to n minus 1. So then here's how you proceed. First of all, you subtract each data pair to create one set of differences. Then find the mean of these differences, and that is our d bar. That's the mean of the differences. And then we find the standard deviation of the differences, and that is s sub d bar, standard deviation of the differences. And then the standard deviation for the test is s sub d bar divided by the square root of n. Again, degrees of freedom is n minus 1. Let us look at a simple example. The table shows the heart rates, the beats per minute of 5 people before exercising and after. Is there enough evidence to conclude that heart rate increases with exercise? We are supposed to use alpha as 0.01. So we begin by subtracting the before minus after, and that would be our D column, our difference column, and it would be minus 62 and minus 63. So then we compute the mean of the differences. In other words, we add up the means or the differences and divide by 5. And so our mean of the difference is d bar, and that is minus 59. And the standard deviation of the differences, s sub d, is 3.39. That's our standard deviation. So when you write our hypothesis, what we are comparing here are the mean heart rate before exercise and the mean heart rate after exercise. And the claim is that before exercise, the heart rate is less than after the exercise. So in other words, before minus after is less than 0. So that means our alternative hypothesis would be, our alternative hypothesis would be mu sub d would be less than 0. And then our null hypothesis is mu sub d equals 0. In fact, in the paired hypothesis test, the null hypothesis compares to mu sub d with 0. So we always have this, where mu sub d equals 0 when we have a paired hypothesis test. So we sketch our t-distribution here, and we have a left tail test with alpha being 0.01, so that's the probability of 0.01 under the curve. And this is our critical value, and we can look it up in the t-table. And so our critical value is equal to minus 3.747 for alpha equal 0.01 and degrees of freedom equals 4. So that's our critical value. So to compute our test statistic, it's d bar, which is minus 59, divided by s sub d, which is 3.39, divided by the square root of n, the square root of 5. That's minus 38.92, so we are way into the rejection region. And when we compute our p-value, with technology in this case, the p-value is less than 0.0001, which is certainly less than our alpha of 0.01. And again, this also leads us to conclude to reject the null hypothesis. In fact, we can even say strongly reject the null hypothesis. Reject the null hypothesis. I mean, this is very convincing to be that far into the rejection region. So we can state our conclusion, number 6. And so our conclusion is that with 5% level of significance, this data does provide significant evidence that the mean heart rate after exercise is higher than the mean heart rate before exercise. In other words, there's strong evidence to conclude that heart rate increases with exercise. So here you have in writing, with 5% level of significance, this data does provide significant evidence that the mean heart rate after exercise is higher than the mean heart rate before exercise. The next step is to find a confidence interval for mu sub d that predicts how different are the two means. So we want to find a confidence interval for mu sub d, the average difference in the population. And so that's simply d bar plus or minus e, the margin of error. And the margin of error is t sub alpha divided by 2 times the samples, sum to the standard deviation of the differences, divided by the square root of n. Now the reason it's a 98% confidence interval is because alpha was 0.01. And remember, we got to balance this with the same 0.01 in the right tail, so that means in the middle we have 0.98. So that's where this 98% comes from. So the margin of error using this formula here is 5.68. So then our d bar plus or minus the margin of error is equal to 59 minus 59 plus or minus 5.68. It's an 8 here. So here then is our confidence interval, which basically says that the mean of the differences before and after, minus after, is between minus 64.7 and 53.3 beats per minute. So the conclusion would be, with 98% confidence, this data predicts that on average, heart rate before exercising is between 53.3 and 64.7 heart beats per minute lower than after exercise. So I wrote the conclusion up here that with 98% confidence, this data predicts that on average, heart rate before exercising is between 53.3 and 64.7 beats per minute lower than after exercise, on average. Here's another example where we're comparing Hampton versus La Quinta Inn. The following data represents the cost of one night stay at the Hampton Inn Hotel and La Quinta Inn hotels for a random sample of 10 cities. So we compute the differences between Hampton and La Quinta, and that turns out to be 31. So then D bar equals 31 divided by 10, or 3.1. And when you do the standard deviation using technology, standard deviation of the difference is that was 9.1098. So then our test statistic is equal to 3.1 divided by 9.1098 divided by the square root of 10, and that is equal to 1.076. That is our test statistic. When we write our hypothesis now, we want to compare the mean price for one night at Hampton Inns and the mean price for one night at La Quinta Inn. So the claim is that the Hampton Inn is not equal to the La Quinta Inn room rate. So we use the Hampton minus La Quinta Inn, mu sub d not equal to 0. So in other words, that is now our alternative hypothesis. Mu, the difference, is not equal to 0. And therefore our null hypothesis is mu sub d equals 0. And let's graph our distribution and region of rejection and find our critical value. So we graph our t-distribution with its two-tailed based on the alternative hypothesis. Degrees of freedom equal 10 minus 1 equal to 9, and alpha 0.05, so alpha divided by 2 is 0.025. And that'll give us critical values of minus 2.262 and positive 2.262. Our test statistic, which we computed up here, is 1.076, and a p-value using technology is 0.3099. So 1.076 is about here. So in other words, we are not in the rejection region for the null hypothesis, and the p-value is not less than alpha, alpha being 0.05. So both of these indicate we failed to reject the null hypothesis. So both the test statistic indicating we're not in the rejection region and the p-value being greater than alpha leads us to conclude that we failed to reject the null hypothesis. So we can state our conclusion, which is, with 5% level of significance, this data does not provide significant evidence that the mean price for one night stay at Hampton Inn is different than La Quinta Inn when compared within the same city. So again, with 5% level of significance, this data does not provide significant evidence that the mean price for a one-night stay at Hampton Inn is different than La Quinta Inn when compared within the same city. So the next question is, continuing with the previous example, what does a question mark confidence interval tell you about price differences between the two hotels? First of all, let's observe that we are dealing here with a two-tail distribution. So in other words, we already have balanced tails of 0.025 each. So we are dealing with a 95% confidence interval. So that's the first observation, which is different from some of the other examples where we had to balance the tail since we are dealing with a left or right tail distribution. Using technology, we determined that the confidence interval at 95% is from minus 3.417 to 9.617 for the mean of the differences. And since this confidence interval includes 0, we can conclude that there is no predictable difference between the price of one night stay of these two hotel chains. So that's a salient observation here, that the confidence interval includes 0. So in conclusion, we can say, because 0 is included in the confidence interval, we can say there's no predictable difference between the price of one night stay at these two hotel chains. Let's look at one more example here. To test the claim that a blood pressure medication reduces the diastolic blood pressure, a random sample of 10 people with high blood pressure had their pressures recorded. After a few weeks on the medication, their pressures were recorded again. Use alpha equals 0.05 or 5% to test the claim that the medicine lowered mean diastolic blood pressure. So obviously this is a case of dependent samples because we're dealing with the same person before and after using the medication. And so the first thing we need to do is we need to compute the differences between the before and the after. So we subtract the after from before. So before minus after. Let's do the differences. So here we computed the difference before minus after. And when we add them all up, that's equal to 59 divided by 10 gives us a D bar of 5.9. So D bar equals 5.9. So let's write our hypothesis. So the claim is that before is greater than after. That means our null hypothesis is that mu sub d equals 0, and the alternative hypothesis is that mu sub d is greater than 0. So we have a right tail distribution. So let's sketch that and put in the critical value. So here's our t distribution. It's right-tailed. There's 0.05 area in the tail, 5%. And so for degrees of freedom of 9, that means our t critical value is 1.833. Define that in the tables, the t-table distribution. So let's compute our test statistic, number 3. And whether we do it by hand or use technology, I use technology in this case. The test statistic comes out to 3.293. And the p-value, number 4, the p-value is equal to 0.0047. So 3.293 with a critical value of 1.833 here tells us we are way into the rejection region. So this value is in the rejection region. And also the p-value is certainly less than alpha, 0.05. So both of these observations lead us to conclude that we reject the null hypothesis. So 5, reject the null hypothesis. So we conclude then, we write our conclusion as follows. So to repeat this, our test statistic is way into the rejection region. The p-value is less than alpha. Therefore, the conclusion is, or the decision is we reject the null hypothesis. And our conclusion is this: with 5% level of significance, this data does provide significant evidence that the mean blood pressure before taking the medication was higher than the blood pressure after taking the medication. So I put that statement here for you. With 5% level of significance, this data does provide significant evidence that the mean blood pressure before taking the medication was higher than the blood pressure after taking the medication. And the last question is, find the question mark confidence interval for the mean difference before and after blood pressure. So first of all, let's remember we're dealing with the right tail distribution, with 5% being in the right tail. Therefore, for the confidence interval, we need to balance it with 5% in the left tail. That leaves us 90% or 0.90 in the middle. So we are dealing with a 90% confidence interval. So that's the first observation. And the question really is, how much does this medicine change blood pressure on average? So when we compute the confidence interval, and I chose to use technology for this one because it's a lot more convenient, a lot faster, we find that the confidence interval for the mu sub d goes from 2.6157 less than mu sub d before and after, before minus after, minus after, less than 9.1843. So in other words, with 90% confidence, we can predict that average blood pressures were between 2.6 and 9.2 millimeter per Hg, higher before the medicine compared to after. So let me write that for you. So the conclusion for the last part is that with 90% confidence, we can predict that the average blood pressure were between 2.6 and 9.2 millimeters of mercury, higher than before the medicine compared to after. So Hg is a chemical symbol for mercury, and it comes from a Latin word hydrargium. This concludes section 9.4.